Hi everybody, it's Professor Mitchell. Today we're talking about section 5.5, trigonometric equations. So this is why we ducked back into section P7 there briefly, just to brush up on solving equations. All right, so there are several different kinds of trigonometric equations. Obviously, a trigonometric equation is going to be any equation that involves a trigonometric function. So here are some of the different tricks that we use to solve those things. All right, so let's have a look. Okay, and I guess this is what I just said to you, right? A trigonometric equation is an equation that contains a trigonometric expression with a variable, such as sine x. And the values that satisfy that equation are called its solutions, just like any other equation. So is it the first example? One of the first examples we're going to look at involves multiple angles. So you'll see what that means. Okay, that is not the first example. Equations involving a single trigonometric function, those are pretty simple. Here is an example. We have 5 sine x equals 3 sine x plus the square root of 3. And it says solve that equation. Now, you're going to see that there are two different things they can ask you to do with a trigonometric equation. They can ask you to find all the solutions. And usually a trigonometric equation has an infinite number of solutions because of the periodicity of the trig function, right? Other times they will just ask you to find solutions, say, between 0 and 2 pi. Okay, and generally these solutions are found in radians. Okay. All right, so what we're going to do with this thing is we're going to first solve it for sine x. So it's almost like pretend that this is the equation 5u equals 3u plus the square root of 3. That's a nice little linear equation. So what you do with linear equations is get all of the variable terms on one side, get all the constant terms on the other side. Okay. So if this was 5u equals 3u plus the square root of 3, the first thing I would do is subtract 3u from both sides, right? So that's what I'm going to do with this. I am going to subtract 3 sine x from both sides. See what they did there? The way that I would normally write it is like this. I would just sneak a 3 sine x underneath each side. And what that's going to give me is 2 sine x equals the square root of 3. So now the only thing standing in my way of sine x being by itself is that 2. So I will divide both sides by 2. And that's going to give me sine x equals square root of 3 over 2. All right, so let's see. So far we have sine x equals square root of 3 over 2. So I'm going to think about my unit circle and think about all angles on the unit circle whose sine is root 3 over 2. Those two angles are pi over 3 and 2 pi over 3, right? You can look on your unit circle and see that those are the two angles between 0 and 2 pi whose sine is square root of 3 over 2. Okay, but since this problem says solve the equation, it does not just say find solutions between 0 and 2 pi. We need all the solutions. This equation is going to have an infinite number of solutions because it also includes anything that is coterminal with either pi over 3 or 2 pi over 3. So the way that you write that is pi over 3 plus 2n pi. So let me see if they attached the, no, they did not. Okay. So sometimes they'll attach a note to this that says, oh, well, maybe I'll attach the note. Here, I thought about trying something different with the pen today and seeing if it made any difference. Okay, so far I can't even speak. Yeah. Oh, stop it. Okay, that's not working at all. So much for that plan. Come on now. Where n is any integer. And if you really want to geek out, instead of writing where n is any integer, you can write this thing. You can write n and then put this symbol, which stands for is an element of, and then this funny looking z stands for integers. So you might see that in your pre-calculus class, just giving you a sneak preview of what that looks like. So what this means is add or subtract any multiple of 2 pi, and that will also give you a solution. For example, if n is 1, then this would say pi over 3 plus 2 pi. And when you get your common denominator and do all of that happy stuff, that's going to give you 7 pi over 3. So 7 pi over 3 means take one whole trip around the circle and then stop in the same place as pi over 3. All right, the next example is solving an equation with a multiple angle. So when they say multiple angle, they mean there's a number attached to the x, right? So this one says the tangent of 2x equals the square root of 3. And notice this time they just want solutions between 0 and 2 pi. So we're not going to have to do that, you know, plus 2n pi or whatever it is, n pi. Okay. There will not be a letter n in the answer for this one. Okay, so the way I like to do these is first I say, since the solutions that we're looking for are between 0 and 2 pi, that means 2x, which is what I'm taking the tangent of, can be between 0 and 4 pi. And the way that I did that was I just took the inequality they gave me and I multiplied everybody by 2. Okay, multiplied that by 2, multiplied this by 2, multiplied everybody by 2. So if x is between 0 and 2 pi, rats, that means that 2x is between 0 and 4 pi. Okay. All right, so what we have to do is figure out all angles between 0 and 4 pi whose tangent is the square root of 3. So I put this little question in here. These angles, these mystery angles that we're looking for, are going to be in quadrants 1 and 3. Do you know how I know they're in quadrants 1 and 3? Give you a hint. What class will you be taking after you take pre-calc? Well, you'll be taking calculus, right? Because all students take calculus. Okay. So the tangent is equal to square root of 3. Square root of 3 is a positive number. The only two quadrants where tangent is positive are quadrant 1 and quadrant 3. Okay. All right, so we need to find these angles now. So hopefully the one in quadrant 1 will be easy. In quadrant 1, it's pi over 3 whose tangent is square root of 3, right? The tangent of pi over 3 is square root of 3. And then in quadrant 3, it's the angle whose reference angle is pi over 3. So let me see if I can kind of, whoops, didn't mean to do that. Okay, so here is my unit circle. There's pi over 3. So the other angle we're talking about is this angle down here, right? And that angle is what you get when you add pi to pi over 3. And that comes out to 4 pi over 3. All right, so far we found two angles whose tangent is pi over 3. Those angles, let me try that again. We have found two angles whose tangent is square root of 3. Those angles are pi over 3 and 4 pi over 3. Okay, but remember we're looking in the interval 0 to 4 pi, so that is 2 full trips around the circle. So in the first trip around the circle, you get pi over 3 and 4 pi over 3, right? You get these two. But then in the second trip around the circle, you add 2 pi to those, okay? So we also get 7 pi over 3 and 10 pi over 3, okay? So there are a total of 4 angles between 0 and 4 pi whose tangent is the square root of 3. Those angles are, I think I have them listed here, pi over 3, 4 pi over 3, 7 pi over 3, and 10 pi over 3. Okay. So the very last thing I'm going to do is say, okay, well, that's nice. So I know everything there is to know about 2x, but what I really wanted to know about was x. So if I divide all of these values by 2, what I get is pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3. So to see how I went from here to here, it might be helpful instead of thinking of this as divide by 2 because they're all fractions, it might be clearer to multiply them all by 1/2. Multiplying by 1/2 is the same thing as dividing by 2, right? So that's the final answer. The 4 solutions to this equation, there are 4 solutions, are pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3. All right, next example, they call this solving a trigonometric equation that is quadratic in form. So what they mean by quadratic in form is that if you made a certain substitution, it would literally become a quadratic equation. So for example, suppose that you took out this cosine x, just the cosine x, not the cosine squared of x, and you replaced it with a u, this equation would turn into 4u squared minus 3 equals 0. And that would be a quadratic equation. Quadratic in the variable u. Okay. All right, so what we have to do now is reach into our bag of tricks for solving quadratic equations. This one is pretty simple. Since they're, well, let's focus on this, on the u form. We'll focus on u. Okay. 4u squared minus 3 equals 0. Because that just has a u squared in it and not a u, we can solve this equation using what's called the square root property. All right, and that is where you start by isolating the u squared. So we will isolate cosine squared x, and the way we'll do that is we will add 3 to both sides. See how they added 3 to both sides, just plus 3 plus 3. And then, of course, we'll divide both sides by 4. And what that is going to give me is cosine squared of x equals 3/4, right? Okay, here comes square root property. I kind of wish I had reviewed this in section P7. I think they went over it there, but I skipped it. I'm thinking of a mystery number whose square is 3/4. The only way that could happen is if the mystery number, be careful, is either the positive or negative square root of 3/4. The positive or negative square root of 3/4. This would be easier to understand if it was just a nicer number. Like suppose this equation said z squared equals 9. Well, the only way z squared can equal 9 is not only if z is 3, but also if z is negative 3. There are two numbers whose square is 9. Okay, so that would give you plus or minus 3. And it's the same for any number that you write here, even if it's not a nice perfect square. Okay, if something squared is 3/4, then that mystery something has to be either the positive or negative square root of 3/4. All right, so we need to find all angles between 0 and 2 pi whose cosine is either √3/2 or negative √3/2. Okay, so that's going to be a total of 4 angles, right? There's going to be one in quadrant 1, and then the corresponding angle in each of quadrants 2, 3, and 4. So this time I'm not paying any attention to all students take calculus because it can be either positive or negative. Okay. So the 4 angles that whose cosine is either plus or minus √3/2 are, of course, pi over 6 in quadrant 1, 5 pi over 6 in quadrant 2. Here, let me try to draw a picture of this. Okay, so here's pi over 6. Here is 5 pi over 6. Here is 7 pi over 6. And here's 11 pi over 6. So it's every angle whose reference angle is pi over 6. All right, next example, using factoring to separate different functions. So they've given me this equation, sine x tangent x equals sine x. And again, they only want solutions between 0 and 2 pi. Okay. So what I am going, let me tell you first what I am not going to do with that. This is what you don't want to do. Do not start by dividing both sides by sine x. That's a very tempting thing to do. I'll talk a little bit later about what would go wrong if you did that. Okay. So what I'm going to do instead is I am going to, I don't know if I would exactly call this standard form. I don't know if that's a real term for what I'm doing here, but I'm getting everything on one side. I'm going to solve this equation by factoring. So I am subtracting sine x from both sides of the equation. Okay, and that's giving me sine x tangent x minus sine x equals 0. Now I am going to factor out sine x, which gives me this. So when you factor out sine x, the other factor is tangent x minus 1. All right, so just like we were just talking about in section P7, they call this the zero product principle. If I'm thinking of two mystery numbers whose product is 0, the only way that could happen is if one of those mystery numbers is 0. So if sine x times tangent x minus 1 is 0, the only way that could happen is if either sine x is 0, and I think what they do at this point is they take this all the way, let me see what I did. Okay, is if sine x equals 0 or tangent x minus 1 equals 0. Okay, either this or this. I wrote it all the way up here because I need a little bit of extra room under that one. Okay. If sine of x equals 0, there is actually only one angle. No, I'm sorry, that's a lie. There are two. I'm sorry. I was thinking of something else. There are two angles in this interval whose sine is 0. Those angles are 0 and pi, right? So the 2 points on the unit circle with a y coordinate of 0 happen at the angles 0 and pi, okay? And then moving over here to tangent x minus 1 equals 0, that of course means that the tangent of x is 1, right, by adding 1 to both sides. Okay, so now let's think about when is the tangent of x equal to 1? Well, one time is in quadrant 1 at pi over 4, right? And then the other time is in quadrant 3, again, because of all students take calculus. The angle whose reference angle is pi over 4. That angle would be 5 pi over 4, right? Okay, pi over 4 in quadrant 1, 5 pi over 4 in quadrant 3. So this equation, again, has a total of 4 solutions. 0 and pi from sine x equals 0, and also pi over 4 and 5 pi over 4 from tangent x minus 1 equals 0. All right, I almost forgot to mention, why would you not want to start this off by dividing both sides by sine x? Well, let me show you what happens if you do that. Let me pick this ugly color here. If I started off by dividing both sides by sine x, what that would do is it would leave me with tangent x equals 1, right? Okay. Well, tangent x equals 1 is right here, so that would give me these two solutions, but these two would have gotten lost because those two values make the sine of x equal to 0, and of course you're not allowed to divide by 0, okay? In general, when you're solving equations, you want to be very, very, very careful about dividing both sides by variable expressions, unless you are absolutely sure that those variable expressions cannot be 0. So let's get rid of this. I don't want to do that. All right, next example, using an identity to solve a trigonometric equation. So this one looks kind of tricky. I mean, you look at this and it's like, oh my gosh, it's the cosine of 2x and then the sine of x. What am I supposed to do with that? Well, I think it would be a little clearer if this 2x was not a 2x, if it was just an x. So the way that we're going to make that 2x into just an x is we are going to use the double angle formula for cosine. Now you may remember that there were actually 3 different versions of the double angle formula for cosine. I am going to use the one that makes this whole entire equation be in terms of sines, only sines. And that identity was cosine 2x equals, cosine 2x equals 1 minus 2 sine squared x. That was one version of the double angle formula. Okay. So now what we have is an equation that is quadratic in form. It is quadratic in sine x, just like that other example we did with the cosine squared of x. And equations like this are practically the whole entire reason that I went over section P7 just before this, because we needed to practice solving quadratic equations. Okay. So if we rewrite this, okay, what they did here was they multiplied both sides of the equation by -1, and the reason they did that was so that their leading term would not have a minus in front of it. It makes it a little bit easier to factor. Okay. So this would be trickier to factor if this 2 sine squared x had a negative in front of it. I wanted to get rid of that negative. Okay. So this is just like factoring 2u squared minus u minus 1. We did an example almost exactly like that in section P7. I think the only difference was this was a plus, if I remember correctly. So you know what? While I'm here, let me just do this. So you solve those by factoring. The only way to get 2u squared would be with 2u and u. 2u and u. The only way to get the 1 would be with 1 and 1. So now I'm going to think about how do I get the minus u. All right, thinking about FOIL. The first is taken care of, the last is taken care of. Now I have to worry about the outer and the inner. So the outer would be 2u, the inner would be u. And the way that I am going to get those to add up to minus u is if this is a minus, which means the minus was here, and if this was a plus, and that plus would have come from here, okay? All right, I think it's a little easier to look at it that way instead of in terms of sine x. So now you'll understand how they got this, okay? That thing factors into 2 sine x plus 1 times sine x minus 1. And that equals 0. So again, the only way that the product of those two things could be 0 is if one of them is 0. If 2 sine x plus 1 is 0, that must mean that 2 sine x is negative 1. That's subtracting 1 from both sides. And then dividing by 2 on both sides, you get sine x is negative 1/2. Now, is this the part where they're going to tell me what x is? Well, probably. So let's, oh, there it is, spoiler. Okay, so why are those the two solutions if sine x is negative 1/2? Well, it's because on your unit circle, first of all, where is sine negative? It's in quadrants 3 and 4. There's negative 1/2, so we're looking here and here. So these two angles both have a reference angle of pi over 6 because the sine of pi over 6 is 1/2. Okay, but I don't want 1/2, I just want negative 1/2. That's why I have to go down here into quadrants 3 and 4. Okay. So two of the solutions are 7 pi over 6 and 11 pi over 6. I believe there is only one other solution. Okay, because there is only one place on the unit circle, one trip around, where the sine of x is equal to 1, and that is right up here, isn't it? When x is pi over 2. So this equation has 3 solutions, 7 pi over 6, 11 pi over 6, and pi over 2. Okay. All right, so now we get into a couple of examples with using the calculator to solve trigonometric equations. So the first example is solve the equation correct to 4 decimal places in the interval from 0 to 2 pi for tangent x equals 3.1044. Okay. So the first thing I will point out, and then when I get to the point where I need to do this, I'll switch over to the calculator. One of those solutions, just one of them, will be the inverse tangent of 3.1044. Now let me draw you a picture before I switch over to the calculator. On the unit circle, there are 2 quadrants in which the tangent is positive. This has come up a couple of other times today. Okay. One of them is quadrant 1. Okay. And then there will be a corresponding angle in quadrant 3. Okay. So this angle, the one in quadrant 1, the value of that angle is literally inverse tangent 3.1044. Okay, because remember, what comes out of an inverse trig function is an angle. And then the other angle will be that angle plus pi, right? Because we need to go down into quadrant 3. So what I'm going to do now is I'm going to go over to the calculator, and I'm going to ask it, first of all, what is the inverse tangent of 3.1044? And that will be one of my solutions, and then the other one will be that number plus pi. So I'm going to go grab the calculator. Okay, so here I am in my calculator. First, I'm going to make sure that I am in radian mode. These problems are all done in radians. I am in radian mode. So now I am going to ask the calculator what is the inverse tangent of 3.1044. So this will be a radian angle. And to 4 decimal places, that radian angle is 1.2591. I'm sorry, 1.2592, right? So that's one of the solutions. And then the other solution is that angle plus pi. If I can find pi on here, there it is. Okay. All right, so my two solutions to 4 decimal places are 1.2592, x equals 1.2592, and x equals 4.4008, right? All right, so we have our two solutions. One of them is about 1.2592, and the other one is about 4.4008. All right, one last calculator example. They want me to solve the equation, correct to 4 decimal places, in the interval from 0 to 2 pi. Sine x equals negative 0.2315. Now with this one, I have to be very, very careful. So I'm going to start off by asking the calculator what is the inverse sine of negative 0.2315, and maybe this time, well, at least not right this second, I won't switch over to the calculator, but the calculator tells me that the inverse sine of negative 0.2315 is about negative 0.2336. Now I need to draw you a picture, because that negative 0.2336 is not going to be one of my solutions. And let me tell you why. Remember, the inverse sine always gives you an angle between negative pi over 2 and pi over 2. So if that angle happens to be negative, I need to switch it over to the coterminal angle that is positive. Okay? So the angle negative 0.2336 radians, I don't think it would not be down that far. Let me try to fix that. Actually, you know what? That's better. It would look something like this. Okay? And it would be measured in the clockwise direction, right? Okay. So I am not actually going to use this as one of my solutions. I can use this to help me get my solutions, but this is not one of the solutions because it is not in the interval from 0 to 2 pi. So the way I'm going to get my solutions is, first of all, my solutions will be in quadrants 3 and 4. Okay, in quadrant 3, what I want to do is start with positive 0.2336. Let me draw a picture of that. I'll pick a different color. Okay. So positive 0.2336 would be like right about here. And then if I add pi to that, that is going to put me down here. And you can see that that angle has the same SINE as the one that I got out of the calculator, right? Because the SINE, the sine, is the y coordinate on the unit circle. Okay? And then to get my other solution, the one in quadrant 4, that one is a little simpler. I'm just going to take the negative 0.2336 that they gave me, and I am going to make 1 whole trip from there around the circle. So I'm just going to add 2 pi to that negative value. And that is going to give me about 6.0496.